We continue our study of the violations of the assumption of the classical linear regression model, and the violation that we now study is called heteroskedasticity. It is derived from two Greek words, hetero meaning different and skedastis meaning dispersion. Assume a population regression function such as yi is a function of x1, x2, x3 and in its stochastic form of the error term sigma I. We've been considering 6 assumptions, and the assumption that bothers us in this section is the fourth one, that is the variance of the error term sigma I square is constant. It is constant for all values of x's. This assumption is known as homoskedasticity, and hence a violation of this assumption is known as heteroskedasticity. Note that what we technically are considering is assumptions of the Gauss-Markov theorem and not assumptions of the CLRM, because we have not considered normality of the error terms in whatever we've done thus far. Now let us take a graphical example. Let us consider a population regression function as we have shown in the graph. For those of you who have carefully noted, this is really a sample regression function that we've drawn because the expected values of y given different values of x are not lying on this red line. However, for illustrative purposes, let us ignore that difference and let us assume that this is a population regression function. So given that this is a population regression function, all points never lie on the population regression function. So there is a stochastic component which ensures that points are off this line. So for any given point, we have an error term which is given by sigma, and here we've represented it as e prime and e double prime for two different levels of x's. So consider at x equal to 10 we have e prime which is negative, and at x equal to 17 we have e double prime which is positive. Now by construction, the OLS estimators ensure that the estimated value of e is equal to 0. What homoskedasticity means is that these e's are almost equal in magnitude, so even those that are negative and positive are almost uniformly distributed around the population regression function. So this need not always hold. We can consider situations wherein the e primes might be lower for lower values of x and higher for higher values of x, as we will shortly see. So here are two graphs. On the left hand panel we see that the sample points are uniformly distributed around the population regression function, and hence this is what we know as homoskedasticity, and this is an assumption of the CLRM. On the right hand side we see that the sample points are diverging from the population regression function as x increases. We therefore suspect that there is some kind of positive heteroskedasticity with respect to x. More specifically, what we really are talking about is conditional heteroskedasticity. That is, expectation of sigma square given xi is not always equal for all values of I. There is obviously then something called unconditional heteroskedasticity, but that really does not concern us in what we are going to do further. We also circumvent this notation by writing sigma with subscript. So we write sigma I square is not equal to sigma j square. This is simply a notation introduced to avoid writing expectation given xi all the time. Now the problem that we will find shortly is that OLS estimators become problematic because they give equal weightage to all samples. Now a sample point such as A, which shows lower variance, is actually more reliable than another sample point which shows higher variance, and hence it should be given more weightage. We will return to this point when we consider the remedies of heteroskedasticity. So take the example of carbon dioxide emission that we have given on our website. So as per capita income increases, the per capita carbon dioxide emission of countries also increases. However, note that for countries having low amount of per capita income, per capita carbon dioxide emissions are also not only low but also less variable. And as per capita income increases, the per capita carbon dioxide emission increases but also becomes more variable. So for higher income countries, it is possible that some of them might decide to invest in green technology and some of them might not, and hence the variation increases. Whereas for low per capita income countries, that is not really a choice, and hence the variation in their per capita carbon dioxide emission is less. Also note that this is cross-sectional data, and it is not surprising because heteroskedasticity is mostly a problem with cross-sectional data and not so much with time series data. Why it is a problem with cross-sectional data is because cross-sectional data pools together samples which are actually from populations of very different sizes. So if you pull together small scale industries and large scale industries, you are going to observe heteroskedasticity because the variation in both of them are going to be very different. Now let us show the problem with heteroskedasticity firstly with a very simple graphical example. Of course, this is a very simplified version, and actual models are much more complicated, but to show the point, let us consider this example of x which takes only two values a and b. Given that x equal to a, the expected value of y is ea. However, it never really takes this point ea, but takes these little points given by the blue dots. So the blue dots are the values that y can take at the when x equal to a, and the expected value is the middle point between the blue dots, which is the red dot. Similarly, we have expectation of b and the two blue dots associated with b. Note that the variation is much lesser when x equal to a than it is at x equal to b, and the line connecting expectation of a and expectation of b is known as the population regression function, or the PRF. This describes the population. However, when we are actually given a sample and not the population, we do not know the value of the PRF, we do not know E of A, and we do not know E of B. We have to estimate all these things based on whatever points are given to us. Take a simplified example that we are given only one of the blue points at x equal to A and one of the blue points at x equal to B. Given this, we obtain the following sample regression functions. These consider any two points at A and B. There are two things that you should note about these four diagrams. One is that the slope of the sample regression function in any of the four cases is never equal to the slope of the population regression function. This is not surprising because we do not really know the expected value, and hence we are not going to obtain the slope as we obtained in the population regression function. But more importantly, what you see is that there is a high degree of variability, right? Because on the top right hand side corner we obtain a very flat line, whereas in the bottom right hand corner we are obtaining a very steep line. This is the kind of problem that we face with heteroskedasticity, in the sense that your coefficient of the population regression function, whose estimate we obtain, is highly variable. And to put it together more formally, the estimates of the regression coefficients are still linear and they're still unbiased. Going back to the previous slide, we see that even though there is a lot of variability, but on an average we will obtain the slope equal to the slope of the population regression function. But what the main problem that we see, that it is no longer a best estimate. That is, there is no longer minimum variance. It is possible to obtain another linear and unbiased estimate which has lower variance than our OLS estimators. Also, that the estimate of sigma I square. Now sigma I square is the variance of the error term, so the estimate of sigma I square is no longer unbiased. When we have a sample, we obviously do not know the value of sigma I square, and we estimate it using a function given by summation of ei square by n minus k, as you have previously seen in another module. However, now this estimate is no longer unbiased, and hence the estimate of variance of alpha and beta are also biased. Because of this problem, the t-test and the f-tests are now unreliable. The problem that we encounter while we talk about detection of homoskedasticity or heteroskedasticity is that the population regression function is not known to us. Hence, we cannot really calculate the error terms from the population regression function, which are given by sigma I square. What we instead have is the sample regression function, and hence error from the sample regression function, which are given by ei square. Hence, the common problem is that we are using ei square as a proxy for sigma I square, and that the true sigma I squares are not known to us. Hence, all the tests that we are going to talk about in this section are going to be probabilistic cases, that we are saying with a probability of 95% that homoskedasticity is not violated. So we divide our tests into two categories. One are specific tests and one is general tests. Specific tests are the tests which assume a particular functional form for the error terms, and the general tests do not assume this kind of functional form. Now, the first two families of tests that we consider are the really old ones, which were given in the 1960s and nonetheless became very popular then. The first is the Park test and the second is the Gletzer test. The common methodology in both these tests is that you run the original regression of y's on the different x's. You obtain the estimates of ei squares for all the different i's, and then you run the regressions. For the Park test, you take a functional form which is log of ei square is equal to alpha plus beta of log of xi plus vi. Xi is that independent variable on which you think that the heteroskedasticity would be dependent. So if you think that the ei squares are going to be dependent on xi, you take this functional form. You might also face the problem that some xi's are negative and hence the log of a negative number is undefined. So you can take another functional form which is log ei square is equal to alpha plus beta xi plus nu I. In contrast, there is another family of tests which is the Gletser test, which instead of taking the square of ei and then taking the logs, it takes the absolute value of ei, and it can take a lot of functional forms. With the two functional forms that we are giving here as examples are ei is equal to alpha plus beta xi plus nu I, and mod of ei is equal to alpha plus beta 1 by xi plus mu I. So in one we are assuming that it is a linear dependence, on the other we are assuming that there is a reciprocal relationship. How we now test for heteroskedasticity is that we assume that the value of beta in any of these functional forms is equal to 0. That is, the ei squares are independent of xi. So our null hypothesis in this case becomes that there is no heteroskedasticity, that is, homoskedasticity is satisfied. However, if we can reject the null, that is, if we can establish that beta is not equal to 0, then we have established that there is a probability of there being heteroskedasticity. We can take any confidence interval that we want, but obviously the preferred ones are 95% and 99%. Now there are some problems that we face with the Park test and the Gletser test. Firstly, they assume a particular functional form for the error term. So in all these functional forms that we've noted here, ei is dependent on xi. However, there might be other independent variables on which the error term might be dependent. So for example, the error term might be dependent on other independent variables such as zi or such as wi, which the Park test and Gletser tests are not capable of handling. So the Park test and Gletser test can only be used when there is suspicion of heteroskedasticity with respect to only one independent variable. Secondly, the error term in these auxiliary regressions, which is nu I, itself might be heteroskedastic, that is, making the result of the T and F test that we've just done unreliable. Now, Gletser's defense to this criticism was that asymptotically these tests are reliable, that is, in larger samples we will find that nu I is not suffering from heteroskedasticity. However, these problems are quite severe and they make the Park and Gletser test very unreliable and not so useful. We hence turn to the next test, which is the Goldfield quant test or the GQ test. In the GQ test, instead of considering the entire sample as one, we run two separate regressions. One is for those x's which have low values and one is for those x's which have high values. So for example, if we consider a sample of 100 and we say that probably the error terms are correlated with this particular x1i, then we arrange the entire sample in increasing order of x1i, take the first few samples and take the last few samples and run separate regressions on both of these. Now the first few samples, which is set 1, and the last few samples, which is set 2, need not be equal in size, and they should neither collectively include all the samples. In fact, if we increase the number of samples that we have dropped in the middle, it increases the power of the test. However, what Goldfield and Quant recommended was that we should take each of these samples to be equal to 3 by 8 of the total sample size. So if the total sample size is 1000, then we should consider 375 samples of the beginning, 375 samples at the end, and we should drop all the samples in the middle. Now the procedure is simple, that you run the original regression on both sets and observe the residual sum of squares. You can obtain the residual sum of squares using either of the formulae that we have previously described, or in any simple econometric package the residual sum of squares would be given to you. Now our null hypothesis is that there is no heteroskedasticity present. Hence the RSS1 should be equal to RSS2. So you set up this F test of RSS1 by RSS2 and you test it for RSS1 equal to RSS2. If you are able to reject the null that RSS1 equal to RSS2, then you can conclude that there is a detection of heteroskedasticity. Note that the degrees of freedom of the F test that we have considered will be n1, n2, that is the n's which we have given by 3 by 8 of n. However, the GQ test itself is not free from problems. The GQ test assumes a particular functional form of the error terms, and hence under a diverse variety of regressions, the GQ test is not always the most reliable of these detection tests that we have considered. So the most reliable test that we out of the four that we've considered is the White's test. Now the White's test is similar somewhat to the Park and Gletzer test in that we run the original regression and we obtain the error terms EI squares, and then we run an auxiliary regression wherein EI square is shown as a function of all the independent variables, and not only those but the squares of those independent variables and the cross products of those independent variables. If we want, we can even take the cubes or the higher powers of the independent variables, but as we increase the number of independent variables in the auxiliary regression, we are quickly losing our degrees of freedom, which can create problems as we will see shortly. From this auxiliary regression, we can obtain the R square, and under the large sample test, NR square, wherein N is the number of samples in the auxiliary regression, follows a chi-square distribution with k degrees of freedom, and hence we can carry out the chi-square test, wherein our null hypothesis is that there is no heteroskedasticity, and if we can reject it, then we obtain the result that there is heteroskedasticity. Note that k is the number of explanatory variables in the auxiliary regression, not including the intercept term, and hence in our present example it is equal to 5. Now White's general test, because of the fact that it is a general test and does not assume any kind of particular functional form, suffers from certain problems. The first is that since we are not assuming any functional form, hence this test has low power. Secondly, it loses number of degrees of freedom very rapidly. As we increase the number of explanatory variables in the auxiliary regression, the value of k goes up, and hence it becomes more difficult to reject the null hypothesis that there is no heteroskedasticity. We now turn to our last topic in the study of heteroskedasticity, that is remedies. Once we have detected that there is heteroskedasticity, what can we do about it? There are three remedies that we study in this module. The first is to take logs, the second is the weighted least squares method, and the third is to revisit the model, that is that there might be a model misspecification. Since model misspecification is something that we have already dealt with in another module, we take the first two cases, that is take logs and weighted least squares. The thing with taking logs is that it compresses the data into smaller values, and in this way it reduces the variability in the values and hence reduces the problem of heteroskedasticity. This is a very ad hoc kind of remedy, but it can be quite effective in several cases. So let us take a graphical example, again the microfinance example, in which we plot profits versus borrowers. So on the left hand panel, when we plot profits versus borrowers, we see that there is probably a problem of heteroskedasticity, that is as the number of borrowers goes up, the profits go up, but also the variability in profits increases. However, now when we take logs of both profits and of borrowers, we see that the problem of heteroskedasticity has been somewhat contained. Now the sample points are somewhat closer to the sample regression function, and hence heteroskedasticity does not seem to be so much of a problem. However, a more formal way of dealing with heteroskedasticity would be the weighted least squares method. Now, before we deal with how to go about the weighted least squares method, we have to find out the functional form for heteroskedasticity. That is, how exactly are the error terms related to the independent variables. On the left hand side, we take the case wherein the EI squares are a linear function of the xi's. So on the diagram, we plot the squares of residuals on the y-axis and we plot xi on the x-axis. So the left hand panel refers to a case wherein EI square is proportional to xi, and the right hand side panel takes the case wherein EI square is proportional to xi squares. We can now use the observed functional form to modify the regression equation. Suppose our original regression equation is yi is equal to alpha plus beta 1 x1i plus beta 2 x2i plus beta 3 x3i plus ei. Now if ei square is proportional to x1i, as we see in the left hand panel of this slide, then we can divide throughout by root of x1i. So you modify the original regression equation and you get a new regression equation in which every term is divided by root of x1i. Another case could be when ei square is proportional to x1i square, which is the right hand diagram of this slide. Then you divide throughout by x1i and you obtain a new regression equation in which every term is divided by x1i. In both these cases, you can observe that the error term is now homoskedastic. Take the second modified regression equation that we have, in which we have divided throughout by x1i, in which variance of ei by x1i will be equal to sigma I square by x1i square, which is 1 by beta, which is constant for all x's. A similar result can even be shown for the first population regression function that we have considered. Note that this is called the weighted least squares method, because while we are dividing by x1i or by root x1i, what we're doing is giving weights to each and every of the samples in accordance with the value of x1i. So if the value of x1i is high, then we are deflating these samples, whereas if the value of x1i is low, we are giving it more weightage, and hence it's called the weighted least squares. Remember that the problem that we originally faced in the OLS estimators was that it is giving equal weightage to all samples, whether they have high variance or low variance. When we are using the weighted least squares method, we are giving more weightage to samples which have low variance and less weightage to samples which have higher variance, and in this case we're getting rid of the heteroskedasticity problem.